the universe is growing larger. Now, when I mention that the universe is growing larger, what exactly am I trying to convey? Well, allow me to reflect on this concept thoroughly because the majority of individuals misunderstand it. They envision everything scattering outward like a detonation, as though all matter is hurtling through empty space. That interpretation isn't entirely accurate, and grasping this distinction matters. Let me analyze this more precisely. Picture possessing a flexible membrane, all right? And you place markings on this membrane. These markings represent cosmic clusters. Now, you pull the membrane apart. What occurs? The markings separate from one another, correct? However, the markings themselves aren't sliding across the membrane surface. The membrane material itself is being pulled apart. That mirrors what's happening with the cosmos. The fabric of space itself is stretching. Cosmic clusters remain mostly motionless within space, yet the gaps between them keep enlarging. Now you might question, well, why should this concern us? That's precisely the issue. Why does it hold significance? And the explanation proves quite fascinating. When Edwin Hubble, a remarkable astronomer, examined remote cosmic clusters, he observed something quite strange. The illumination arriving from these clusters had shifted toward the red portion of the color range. We refer to this as redshift. And what does this indicate? Well, it indicates these cosmic clusters are traveling away from our location. That alone isn't particularly astonishing. You'd anticipate objects moving around within the cosmos, but here's where it gets intriguing. The greater a cosmic cluster's distance, the more rapidly it's retreating from us. And not merely somewhat quicker, substantially quicker, proportionally quicker. This constitutes Hubble's law, and its elegance lies in its straightforwardness. If you consider a cluster at, say, 1 megaparsec distant, that's approximately 3.26 million light years. It's retreating from us at roughly 70 kilometers each second. Now consider another cluster positioned twice as remote, and it's retreating at double that velocity, 3 times the distance, 3 times the velocity. It's an elegantly simple relationship, but now here's where it becomes fascinating. If this pattern holds true across all distances, then at some specific distance from us, the recession speed, the pace at which something retreats, matches light's velocity. And if something lies even further than that point, it would be retreating faster than light travels. Now you might protest, hold on, nothing outpaces light. Einstein established that. And you're correct. However, this situation doesn't contradict Einstein. This represents something distinct. You understand, Einstein established that nothing can exceed light speed through space locally. Nothing can zoom past you faster than light. However, the cosmos' expansion isn't something moving through space. It's space itself stretching. It's a fundamentally different phenomenon. Consequently, distant cosmic clusters can retreat from us faster than light without contradicting relativity whatsoever. That's the elegant aspect of comprehending precisely what Einstein intended. So, let's determine where this boundary exists. We term it the Hubble sphere. Using light's velocity, approximately 300,000 kilometers divided by the Hubble constant, we arrive at roughly 14 billion light years. That's the distance required before something retreats faster than light. Now, you might assume, okay, so beyond 14 billion light years, we're incapable of observing anything, correct? But that's not entirely accurate either. And this is where matters become genuinely fascinating. You understand the cosmos has been stretching for approximately 13.8 billion years. However, the illumination we receive from remote cosmic clusters has been journeying toward us for billions of years while the cosmos stretched around it. Consequently, a cluster that appears to be 12 billion light years distant because its light required 12 billion years to reach us is actually much, much farther removed. Now, by the moment that illumination reaches us, that cluster might be 20, 23, perhaps even exceeding 25 billion light years away. There's another boundary we need to discuss. It's termed the cosmic event horizon, and it's approximately 17 billion light years distant. Now, here's what this signifies. Any illumination emitted right now at this precise instant from beyond that distance will never arrive at our location. Never. Regardless of how extended we wait, it's not like it will require a billion years to reach us. It will never reach us. This is because the cosmos stretches faster than illumination can traverse toward us. And here's the astonishing part. We inhabit an accelerating cosmos. It's not merely stretching. It's stretching at an ever-increasing rate. Approximately 5 or 6 billion years ago, the cosmos' stretching began accelerating. We're uncertain why. We label the cause dark energy, but honestly, we lack understanding of its nature. We lack understanding of its nature. Isn't that remarkable? Here we are believing we comprehend so much about the cosmos, and we lack understanding of what 68% of it consists of. So the cosmos is accelerating in its stretching, which implies that cosmic event horizon is approaching us in a manner. It's not that it's contracting toward us, but it's contracting regarding the quantity of cosmic clusters we can ever observe or exchange messages with. Gradually, the cosmic event horizon will shift inward, and clusters that we currently observe will eventually cross it, and we'll never observe them again. Now allow me to explain why this matters regarding extraterrestrials. Let's assume somewhere throughout the cosmos there exists an intelligent civilization. Perhaps they inhabit a planet circling a star in some remote cosmic cluster. They possess the identical physics we possess. They cannot exceed light speed. They might attempt to dispatch us a communication, a radio transmission, whatever. However, if they lie beyond that cosmic event horizon, their communication will never arrive at us ever. However, wait, there's additional complexity to consider. Even if they're closer than the event horizon, even if they could theoretically reach us, this complication persists. Allow me to pose a question. If an extraterrestrial civilization desired to visit us, what would they need to accomplish? They'd need to board a spacecraft and journey through space toward us at some speed less than light's velocity, correct? That's within their capability. They cannot exceed light speed through space. Now envision they inhabit a cluster that's retreating from us at say 50,000 kilometers/SCS. They're only moving through space at say 1,000 kilometers relative to their own cluster. However, relative to us, they're moving away at 50,000 kilometers per second plus some minor component of their own movement. They might be capable of traveling faster than 50,000 kilometers/. Certainly. However, can they travel faster than light? No. So even if they decided to journey toward us, they'd be struggling against the stretching of space itself. The space between us and them enlarges faster than they can traverse it. Consider it this way. Let's assume they're 1 billion light years distant. They desire to reach us. They board their spacecraft and journey toward us at 90% light speed, which is extraordinarily fast, something we could never accomplish. However, during the time required for them to travel 1 billion light years at that velocity, the cosmos has stretched. The separation between them and us has enlarged. They're attempting to reach a shifting target that retreats faster than they can approach it. Now, we lack understanding of how intelligent civilizations actually spread throughout the cosmos. We lack understanding if they even desire to spread. However, the cosmos is stretching, particularly this accelerating stretching, presents a fundamental obstacle. It's not merely a practical obstacle. Oh, space travel is challenging. It's a physical obstacle embedded within reality's very structure. This returns us to the original inquiry. Where are the extraterrestrials? And one response is simply this: the cosmos stretches too rapidly. Even if life has emerged elsewhere, even if civilizations exist out there far more advanced than us, they're confined within their own cosmic region by the cosmos' stretching. We're all separated from each other by the straightforward fact that space itself stretches. Now, there's another perspective on this too. Within an accelerating cosmos, there exists a boundary to how much of the cosmos we'll ever be able to observe. Envision in 1,000,000 years, 1,000,000,000 years, 1,000,000,000,000 years into the future. By then, because the cosmos accelerates, we'll be able to observe even fewer cosmic clusters than we currently observe. Clusters will vanish from our sight, and from their viewpoint, will vanish from theirs. Eventually, it's possible that our cluster will be the sole cluster visible from Earth. Everything else will lie beyond the event horizon. You understand? I find this remarkable. Here's something appearing so straightforward. Space stretches. And from that straightforward fact, we derive this profound outcome. The cosmos separates us. It isolates us. We're confined within a bubble of observable space, and we can never venture beyond it. However, let's examine this more thoroughly. Is this genuinely a novel concept? Well, not entirely. We've understood the cosmos stretches since the 1920s. We've understood about the event horizon for some time. However, here's what's fascinating. For an extended period, physicists hoped that perhaps we were mistaken about the acceleration. Perhaps the cosmos would eventually decelerate. Perhaps eventually we could reach those remote cosmic clusters. However, the observations are fairly unambiguous now. In 1998, scientists examined remote supernovae. These are detonating stars so luminous you can observe them from tremendous distances. They discover these supernovae appear dimmer than anticipated. And what does dimmer indicate? It indicates they're more distant than they ought to be. In the sole manner this makes sense is if the cosmos' stretching has been accelerating. The cosmos speeds up. There's something termed the Hubble tension. Now we gauge the cosmos' stretching rate through two distinct approaches. One approach involves examining nearby cosmic clusters and measuring how swiftly they're retreating from us. Another approach involves examining the cosmic microwave background, the residual illumination from the Big Bang, and calculating what the stretching rate ought to be based on early cosmos physics. And these two approaches yield differing results. The direct measurements indicate the cosmos stretches faster than early cosmos physics predicts. We lack understanding why. That's fascinating. Something eludes our comprehension. And this is where I want to emphasize something about scientific inquiry. Individuals occasionally imagine scientific discovery is complete. We comprehend everything, yet we don't. Genuine mysteries exist. The cosmos' acceleration. Why does it accelerate? Dark energy. What is it? The Hubble tension. Which of our measurements is inaccurate? These represent genuine, unresolved inquiries. Now, some individuals have speculated about additional outcomes of this cosmic stretching and acceleration. One fascinating consideration: if the cosmos keeps accelerating, eventually all cosmic clusters beyond our local gathering will vanish. Our Milky Way and the Andromeda cluster will remain isolated, and the intelligent beings inhabiting that distant future won't be able to recognize that a cosmos exists beyond their own cosmic vicinity. They'll gaze outward at the sky, observe only darkness, and they might conclude they're isolated within a static, unchanging cosmos. Isn't that remarkable? A future civilization possessing superior instruments compared to us might actually comprehend the cosmos less than we do, simply because the stretching will have concealed the proof. However, allow me to step back. I don't want to become excessively philosophical. Allow me to share what I believe is genuinely fascinating about this. The cosmos is immense. This represents something we need to comprehend deeply, not merely intellectually. It's not merely immense, it's incomprehensibly immense. More stars exist throughout the cosmos than sand grains on every shoreline across Earth. Yet, due to the stretching, due to this acceleration, most remains unreachable. Most will always remain unreachable. And this is embedded within the physics. It's not a technological deficiency or imaginative limitation. It's reality's fundamental nature. Now, if you inquire of me, does this indicate we're isolated? I don't believe that's the appropriate inquiry. I believe the inquiry proves more fascinating. What does the cosmos' structure reveal about separation and interaction? And the response indicates space itself prevents us from interacting. Not because distances are too vast in an absolute sense, but because space keeps stretching, because the stretching accelerates. So here's something to contemplate. If extraterrestrials attempt to reach us currently from some remote cosmic cluster, they're squandering their effort. Even if they race toward us at nearly light speed, if they're sufficiently distant, the cosmos stretches faster than they approach. They'll never succeed. The cosmos will maintain their separation. Conversely, if we desire to attempt reaching other cosmic clusters, if some future civilization decided they wanted to expand throughout the cosmos, they'd encounter the identical obstacle. The stretching would oppose them. And if they delayed excessively, if they delayed millions or billions of years, the opportunities would vanish. The event horizon would shift. Cosmic clusters currently visible and reachable currently would become invisible and unreachable. This represents a peculiar aspect of the cosmos. It's almost as if an opportunity window exists for civilizations desiring to expand beyond their local gathering. And that window gradually closes because of the acceleration of the stretching. That window definitely gradually closes. For any civilization in the distant future, most of the cosmos will lie beyond their reach. You understand, when I contemplate this, it makes me value what we can observe currently. With contemporary instruments, we can observe billions of cosmic clusters. The Hubble Space Telescope can observe cosmic clusters billions of light years distant, and those cosmic clusters retreat from us. In a sense, we're fortunate to inhabit an era when we can observe so extensively. In 1,000,000 years or 1,000,000,000 years, Earth's future inhabitants won't be able to observe nearly as extensively. The cosmos will have concealed itself. Is this disheartening? I don't believe so. I believe it's fascinating. It serves as a reminder that the cosmos functions according to rules, mathematical rules, physical rules. And from those straightforward rules emerge outcomes shaping everything, including the possibility of interaction between civilizations. And if the outcome indicates separation, if the outcome indicates we're divided from most of the cosmos by the stretching of space itself, then so be it. That's reality. That's how the cosmos actually functions. I believe there's something remarkable about comprehending this. We don't get to select the cosmos we inhabit. We get to comprehend it. And comprehending that we're separated by the stretching of space, comprehending why the cosmos manifests as it does, comprehending that this separation isn't a deficiency but reality's inherent characteristic, that represents understanding, and understanding always holds value. So when someone next inquires why haven't we received extraterrestrial communications, you can explain the cosmos itself prevents interaction. The stretching of space, particularly this accelerating stretching, separates cosmic clusters from each other. It's not a mystery solvable by more intensive searching with superior instruments. It's a fundamental property of the cosmos.